Hello everyone, I am so glad to present our paper to you. My name is Kamyar Nasiri and Dr. Kamaledin Ghiasi-Shirazi is my co-author. Our paper is about a new activation function called PowerLinear, which can be applied to the first layer of CNNs. Let's start. CNNs are a class of deep neural networks that process imagery data. They utilize the convolution layer as the main operator, which mimics primary visual cortex cell operation. CNNs use the inner product operator as its main computational core to measure the similarity between input image patches and some filters. The inner product is a linear operator and it is not capable of learning complex features. One way to overcome this problem is accompanying convolution layers with nonlinear activation functions. Another remedy is to replace the ordinary convolution operator with more complex operators. For example, network replace the inner product operator in convolution layers with multi-layer perceptron. Another work is SIMnet architecture that replaced the inner product operator in the convolution layers with an inner product in feature space. SIMnet architecture was introduced based on two fundamental operators. One operator is a substitute for the inner product operator, and the other one is a replacement of nonlinear activation functions and pooling layers. Kernel pooling was introduced to capture high-order nonlinear interactions of features in the kernel form. Another work was convolutional neural networks that are as a generalization of CNN using kernel methods. One way to increase the capability of models and learn more complex features of input images is by applying a nonlinear activation function on top of the convolution operator. Sigmoid and tangent hyperbolic functions were used widely in neural network models. However, both sigmoid and tangent hyperbolic functions have the saturation problem. The saturation of activation functions causes the vanishing gradient problem to happen. On the other hand, ReLU solved the saturation problem in the positive input region of activation functions, which paved the way for deepening the neural network models. Saturation problem remains in the negative inputs region of the ReLU activation function. So to solve this problem, several generalizations have been introduced. For example, leaky ReLU activation function. In this paper, we introduce a class of activation functions that have non-zero gradient values in both positive and negative inputs region. Here we use the polynomial kernel function for generalizing the dot product operator in activation layers. Even PowerLinear activation function, which is a branch of PowerLinear activation functions, provide practical usage. For example, consider a white horse picture on a black background. And that this image had been trained with commonly used activation functions. The trained model cannot easily diagnose the inversion of the original image. However, a network equipped with the even PowerLinear activation function can recognize the inverted image as accurately as the original image. Kamaledin Ghiasi-Shirazi introduced two generalizations of the convolution operator that increase the capability of CNN architectures to learn more complex features. In this paper, we just need to know about the first generalizations. First generalization, say the convolution operator in CNN can be generalized by substituting the inner product with a positive definite kernel function. Let's see the PowerLinear activation function. I want to just talk about polynomial kernels which were most widely used in the kernel methods. We will introduce a generalization of a convolution operator using polynomial kernels. Polynomial measure convolution can be implemented by applying the Powell activation function. Odd extension of this function is a monotonically increasing function and therefore a valid activation function according to first generalization that I introduced before. Even extension of the PowerLinear activation function can be written as this written formula. It is a composition of the polynomial kernel and the monotonically increasing functions. As you can see here, PowerLinear activation functions have two branches, even polylinear activation function, odd polylinear activation functions, and these are the diagrams of these activation functions. Well, as you can see here, even polylinear activation function is an even function, and the same points in the negative and positive regions have same value of output. For example, if you can see here, positive one and negative one have similar values as output. And this is the main feature of even polylinear activation function that make it remarkable among other activation functions. And as you can see, the odd polylinear activation function is an odd function that the output of negative and positive inputs have the same magnitude but with different signs actually. And this is also important to see that this is a new idea, and previous activation functions could not have not this feature that our activation functions have. Polylinear activation functions are zero-centered and differentiable at all points. They do not eliminate the activity of any neuron. I mean, they direct the activity of neurons with negative outputs toward non-zero values. Let's go to experiments. Even polylinear activation functions will be applied on just the first layer of CNNs, as I told you. Even polylinear activation function is similar to the performance of the ReLU activation function in terms of classifying normal datasets. Normal datasets are datasets such as MNIST, CIFAR10, and SPHN. At first, we examine the general functionality of our proposed activation functions. Basically, our proposed class of activation functions can be used in rudimentary and basic CNN architectures. We implemented ResNet 18 architecture by applying the ReLU activation function on the output of each convolution layer. In the next experiment, we examine the performance of even polylinear in the same condition as previous experiments. However, we only used the power 2 of even polylinear activation functions and applied that on the output of the first convolution layer. You can see the result of them here, and you can see there are no fundamental and main differences between the results of ReLU and even polylinear activation functions. Another experiment is to show the main functionality of even polylinear activation functions. Uh, they have the ability to activate equal value positive and negative inputs with the same output value. The value of the negative slope is same as the value of the positive slope in the positive input region. So grayscale images, uh, in the grayscale images, white pixels can be activated with the same value as black pixels. So we want to compare this experiment with another experiment that we implemented, again ResNet 18, and set even polylinear activation function on the output of the first convolution layer and ReLU to the others. We selected normal training data of the MNIST dataset as the training dataset. The accuracy of testing our model on the inverted MNIST test came to 99.48%, with the same accuracy as normal dataset. As you can see here, normal datasets using ReLU on the all layers of convolution gives us around 99%. However, when we inverted data, we got 11%. And if we use even polylinear just at the first layer of CNN, we can see that we have the same percent in the inverted data. Let's talk about the SVHN. SVHN is a colorful data set. So we converted it to grayscale image. The grayscale SVHN has both black digit images on the white background and white digit images on black background. So the model that includes ReLU activation functions only will diagnose white digits on black backgrounds as well as black digits on white backgrounds. So they're somehow persistent against the inversion of grayscale image. Well, as you can see here, a sample of SVHN datasets. Uh, this image shows number 5, which is the first train image of SVHN dataset. It should be first converted to grayscale image, and after that this grayscale image should be inverted. So this part of experiments contains two main steps. First of all, image datasets should be converted to grayscale, and then the result should be inverted. So as you can see, the result of our training was not really different with the ReLU activation functions that I showed this in last slide. Thank you for your consideration, and goodbye.